right, so as I said, the new slides focus even more strongly on the following game. You know, I'm big on games, and just to let you know that this isn't completely off the wall. I was remembering that my father is big on, it was a big researcher in greedy algorithms, and it was called the field called matroids, and the definition of a matroid is that it has the same swapping in, swapping out of solutions, and the same idea that this game has. So what is the game? The first player is the algorithm, and he provides a t - 1, which are all the choices made up to time t - 1. So in this picture here, you can see that based on its greedy criteria, the algorithm first considered objects 5, 7, 9, and 3, and based on its greedy criteria, based on the algorithm, it's decided to irrevocably commit to all except object 7, which it rejects. So those decisions cannot be undone. Now the rest of the objects it hasn't seen yet. It knows nothing about. It hasn't made a decision about them. And what the algorithm does is really simple and sort of dumb, and so we're going to have two other players. We're going to have a fairy godmother and a prover, and he doesn't know about them. They're going to do lots of work that he's not part of, but they watch over him. All right, so our next player comes in, is the fairy godmother, and she's going to provide a full solution that extends what the algorithm has done. Is consistent with what the algorithm done. So what do we mean by that? We mean that even though the algorithm has made these irrevocable decisions specified by at - 1, it's still possible that he produces this full solution. And why is that? Well, because the decisions that the algorithm has made are that the solution fairy godmother gives are consistent with those. So we might say here in formal math, we say for every object in the input, if the algorithm has made a decision about it, then the solution of the fairy godmother on the objects is the same as that for the algorithm. On the other hand, the fairy godmother has a full solution, so she specifies a decision about all the objects that the algorithm has not seen. And one thing we're going to stress is she doesn't make them in a particular order. It's just that she's made a decision about these. All right, so those are the first two rounds. And what is this solution that she's holding? Ideally, what she's holding is an optimal solution. And if it is, then we say it witnesses the fact that the algorithm hasn't gone wrong. How does she find it? She uses some magic to find it. We don't, and the algorithm doesn't know about it. And as I said, we're relaxing the game to require that the solution she gives is not optimal. But if she does give an optimal solution, then what we say is it witnesses the fact that the loop invariant is true, right? The loop invariant says we haven't gone wrong. There's at least one optimal solution that extends the choices made by the algorithm, and the fairy godmother is holding one such optimal solution, and because she has it, we know the loop invariant is true, right? Right, then after that, then it's now time t, and the algorithm can make the next time step. And you see these look the same, but here, watch object 6. The algorithm will make a decision about some next object. It will commit to it, And that's great, but one of the problems is you see that the fairy godmother, maybe her decision about that object is different. And so the solution that the fairy godmother has no longer extends what the algorithm has done. And so that's a problem, right? Because they made different decisions about object 6. So the bridge, this solution has been burnt. We no longer can consider, the algorithm can no longer consider the solution that the fairy godmother is holding, right? So let's now consider sort of our role. Our role is to be the prover, which needs to produce a new solution that extends both what the algorithm has done up to time t-1, but also is consistent with what the algorithm does at time t. And so what the prover produces, which we're calling st, we're going from the fairy godmother has st-1 to the algorithm produces st, witnesses the fact that the algorithm still, as of time t, hasn't gone wrong, right? And one of the requirements is that the solution he produces has to be at least as good as the solution that the fairy godmother provided, right? So here we say, if we're trying to maximize the value of a solution, then the value of the prover's solution is at least as good as the value of the fairy godmother's solution. And this means that if the fairy godmother's solution was optimal, then so is the prover's. Right now, how does the prover get his solution? He doesn't actually have any magic, right? So what he's going to do instead is he's going to just make small massage what the fairy godmother has, make small changes to produce his solution. And remember, when we were doing loop invariants, you don't want to dive in and try to get the loop invariant true in the middle of the computation. You have to use the fact that the loop invariant was true before, right? We use the fact that there was an optimal solution consistent with at-1 in order to get it to be true for time at. And so he just makes simple changes, right? So what are those changes? Well, the first obvious change is not to mess up being consistent with what the algorithm during the first t-1 steps. And then he has to be consistent with what the algorithm did in time t. So when producing this solution st, she has to change that the algorithm rejected object 6 and say, now we have to accept object 6. But if the prover just makes this one change, then maybe the value of the solution isn't as good as it was before, or maybe it's not valid anymore, right? So if, for example, if he suddenly commits to, that the fairy godmother was rejecting this lion and the prover accepts this lion, well, then it's no longer acceptable to have zebras, right? So we're going to have to, the prover is going to have to change some of the decisions on other objects from the future. Here, object 8 is being switched from being committed to being rejected. Maybe that's a zebra that we're no longer accepting because we took the lion. Right now, the hardest part of the prover's job is going to be to find these objects 8 that he's going to change the solution to. And a common problem in students' answers is they will say, well, let object 8 be the next object that the fairy godmother considers. And that's where I said the fairy godmother doesn't have any order to its decisions. We have to somehow come up with another way of describing what object A is that we're going to change. We may change a number of objects, or maybe it's just one. But anyway, when the prover does produce this optimal solution consistent with what the algorithm has done at the time t, that then maintains the loop invariant, right? So what we're proving is if the loop invariant was true for time t minus 1, and the algorithm makes another decision, and the prover changes what the fairy godmother is holding, then we can get that the loop invariant is true at time t. And as we said, the requirement is that what the prover holds is at least as good. And here's the whole game, so you can see it all at once. And